Hello, and welcome to a video that I'll say is an addendum, or a video that is extra content for my statistics courses. I wanted to do a couple more problems with Module 6. Specifically, I wanted to do the last 2 pages in the Module 6 notes. So page 9 and 10 that will also go over some binomial examples. At this point, hopefully we had covered this in class, but I wanted to do a couple more recorded so that you can have more experience and you can have a bigger wealth of knowledge or a bigger wealth of material that you can refer to if you have any problems with these kinds of questions. So what I'm going to do today, I'm going to work through page 9 and 10 here, one with an airline and another one with covering their mouth, or people covering their mouth when they're sneezing. And I'm not going to do my writing tablet, so I'm going to try to have it typed out as I have these answers here. I'm going to see what I can do to make this as nice as I can. Real quick, to cover what we're about to do here, these are going to be examples of a binomial experiment. And for both of these, we're basically going to talk about why they're going to be considered binomial experiments, and then how do we calculate the different binomial probabilities. So, let's start off here with the airline. According to an airline, flights on a certain route are on time 75% of the time. Suppose 10 flights are randomly selected, and the number of on-time flights are recorded. Okay, so our first thing to do is to explain why this is a binomial experiment. So what we want to do is hit the 4 benchmarks that help us define if something is going to be binomial. And we have an acronym called BINS that we can use to help us with this. That's B-I-N-S. I'm going to go through those one by one. All right, so we have B. All right, so B in BINS is going to correspond to the binary outcomes. Whoa. So B in BINS is going to refer to the binomial outcomes, or binary outcomes that we have in an experiment. So what that means is that we're looking for the different possibilities that we can have from this experiment. In this case, we're talking about flights being on time. So for us, our binary outcomes are on time or not. Those are the 2 things that can happen in this experiment. Because we have that, we can consider it to be binary. Our next part of the acronym I stands for independent. And this is where we need to confirm that the trials in the experiment, which in this case are the flights, they're independent of one another. So we don't have anything in the description itself that explicitly states that. However, we can say something along the lines of, we can safely assume that the flights are independent of one another. We could say something similar to that. So, we're not exactly sure, but it's probably likely that these flights aren't really influencing each other too much. That's usually the one that we kind of have to be hand-wavy a little bit about. The third condition, N, stands for the fact that the N value, or your number of trials, needs to be fixed. So N is fixed. So here it says, according to an airline, flights on a certain route have a time of 75%. Suppose 10 flights are randomly selected. That's our N. So N is equal to 10 flights. So that means N, the number of trials, is explicitly fixed at the beginning of the experiment. So we're not just going to haphazardly go around until we get a certain value. Lastly, we have S, which stands for the same probability, specifically the same probability of success. Well, let's fix that. Probability. Same probability of success, and it does give us in the description that they are on time 75% of the time, so we have that P is equal to 75%, or 0.75. So that's going to be our probability of success. We have all of these conditions met, so because I have B, I, N, and S, I have all of them met here, so we're all good. In these situations, if you ever do need to refer to why something is binary, don't just list the things like, say, B is binary, I is independent, N is fixed, N is the same probability. Don't just list those four. At least talk about what they are, like I did here with saying N equals 10, P equals 75%, binary outcomes because it's on time or not. Say something that describes why it meets all those conditions. Now that we've confirmed that it is binomial, what we're going to do is calculate the likelihood of certain probabilities here. First, we're going to find and interpret the probability that exactly 6 flights are on time. In order to work with these, we can work with them by hand, but what we're going to do is our TI calculator here, because there are a couple functions that we can use. And I've already gone through this, hopefully in class, and there's also a video that goes through this separately, but I'll talk about it briefly here. The two functions that we need are in the distribution section of your calculator. You'll see distr above vars. So what we need to do is hit second vars. And we'll see stuff like normal PDF, normal CDF, inverse norm, etc., etc. And what we want are the functions that start off with binom, or binomial. And if we scroll down far enough, we should see Binomcdf and Binomcdf. Likely here on A and B on your TI calculator. They may be, maybe not as far down. Binomcdf, this is the binomial distribution, and it's to find the probability of exactly a certain amount of successes. So if we're looking for explicitly the likelihood of getting 10 successes out of 20, or 13 successes out of 15. If I'm looking for an exact amount of successes, that's what Binomcdf is going to do. Binomcdf, C here is going to stand for cumulative, which means that it'll actually add multiple probabilities together. It will have the probability of a certain number of successes and any value below that. So it finds the likelihood of 0 up to whatever amount of successes I want to indicate. For example, if I'm trying to find the probability of less than or equal to 4 successes, which would mean 0, 1, 2, 3, or 4 successes, I can simply do Binomcdf and it'll combine all of those. Whereas if I did Binomcdf, I'd have to do it one at a time. In this circumstance, we have find and interpret the probability that exactly 6 flights are on time. That's our key there. So because we have exactly 6 flights, then that means we're going to use Binomcdf. So I'm going to start typing this in as we go. So I'm going to use Binomcdf. When I run Binomcdf, it should ask us for 3 prompts. If it doesn't have the prompts for the wizard, then you just need to put the values in the correct order. And when we paste this, you'll see that with commas. It'll ask us for trials, which is N, P, which is the probability, and X, which is the number of successes. So NPX. Here are the trials. There are 10 flights that we're doing. Each flight has a probability of success of 75%, as given in the description. And in this case, we're looking for exactly 6 successes, so my X value is 6 successes. If I paste that, what I have over here, I have Binomcdf of 10, 0.75, 6. That's what I'm trying to find. And when I run that on my calculator, I get approximately 0.146-ish. So I'll say 0.146. Or as a percentage, 14.6%. So that would be my likelihood. If I need to interpret this, I should be able to interpret this probability in a similar way that we've interpreted probabilities in the past by putting it in terms of what a percentage is supposed to mean. I'm going to say something along the lines of, if we were to repeat this experiment 100 times, this experiment being taking 10 flights and finding the likelihood of 6 of them being on time, I'd expect say exactly 6 flights to be on time in about 15 of those repetitions. So if I did this experiment 100 times where I took 10 flights, saw how many of them were on time, I'd expect about I'd expect 6 flights to be on time in about 15 of those repetitions. So that's how I'll interpret that probability. And that's how we'll tend to interpret the probability moving forward. The next one's a little bit different. Notice it says find and interpret the probability that fewer than 6 flights are on time. There's a couple different ways to do this. One way you can do this is by doing Binomcdf and finding the probability of each of the trials or each of the successes individually. Since it says fewer than 6, what that really means is less than or equal to 5. Fewer than 6 are numbers like 0, 1, 2, 3, 4, and 5, not 6. So what I could do is Binomcdf of 10 trials, 0.75, comma 0. That'd be the likelihood of 0 successes, plus Binomcdf of 10, 0.75, and 1, plus Binomcdf of 10, 0.75, and 2, plus etc., etc. I could do this all the way up to Binomcdf of 10, 0.75 up to 5 successes. I could do all of that if I wanted to. This would work just fine. If you notice, though, that will take quite a bit of time. So there is a little bit of an easier way, something that's a little more efficient. And what we're going to do instead, so we can say answer can be represented like this, or the answer could also be represented instead by doing one Binomcdf function, because remember CDF is cumulative, and say, okay, find all the probabilities up to, so if with 10.75 up to 5. This will take all the probabilities of 0, 1, 2, up to 5 and put them all together into 1. That's what CDF is. This line of functions is exactly the same thing as Binomcdf up to 5. That is located in the same place, so I'd say second, vars, and we'll see it here on B. If I run that, it asks us for the same exact prompts, the trials, the trials of 10 flights, 0.75 probability of success, and 5, up to 5 flights being on time. If I run that, I get an answer of 0.078, or 7.8%. So that would be my probability. This would be the same answer as if I did each of these Binomcdfs separately and added them all together. When I would interpret this, I would interpret it in the same way that I did in the previous problem. I'd basically just take this, copy it here, and instead say I'd expect less than 6 flights to be on time in about, we have 7.8%, so about 8 of those repetitions. So that's what I would expect. All right. So far what we have the first couple questions here done. We have for B and for C. The rest of these are going to follow along the same lines, but I'm still going to go through them so you can get some extra practice and see some more examples of them. Find and interpret the probability that at least 6 flights are on time. Well, again, this can be done in a couple ways. We can do this because at least 6 means 6, 7, 8, 9, or 10. I could do this by doing Binomcdf of 10, 0.75, and 6, plus Binomcdf of 10, 0.75, and 7, plus Binomcdf of 10, 0.75, and 8, and you get the gist. So I could do this all the way up to the total number of successes. Or, as you may expect, there's going to be a faster way of finding this answer. Instead of doing each of these individually Binomcdf, what we could alternatively do is do it all at once and be a little bit more sneaky about it. I'm trying to extend this out. There we go. I could be a little bit more sneaky about this by using Binomcdf. Unfortunately, Binomcdf, if you notice, has a little bit of a restriction. I can't exactly tell it to go from anything but 0 up to something. It only goes from 0 up to whatever number I indicate for a number of successes. I don't want to include 0 here. I only want 6, 7, 8, 9, etc. Well, what that really means is that I need every probability for each value except for 0, 1, 2, 3, 4, and 5. I want the probability for the rest of them. So what that means is that I can solve this by doing a complement instead. I could do 1 minus Binomcdf of 10.75 up to 5, which is what we did in the previous problem. This way, Binomcdf finds a probability of 0, 1, 2, 3, 4, or 5 successes. And if I take that probability away from 1, I am left with the probability of everything else, which would be the probability of 6, 7, 8, 9, or 10 successes. Since we already have this from the previous answer, I could just say 1 minus 0.078 approximately, and that should give us 0.922 or 92.2%. So that would be my answer there. I could then interpret it yet again by doing the same exact sentence, saying, if I did that experiment 100 times, I'd expect, in this case, we're looking at more than 6, or at least 6 flights to be on time, and we have 92%, so I'll say 92 of those repetitions. Thirdly, or I guess this would be the fourth question that involves actually calculating. Find and interpret the probability that between 4 and 6 flights are inclusive are on time. Now this one you can still do with Binomcdf, it's just a little bit weirder. I'll do both representations. In this case, I think Binomcdf is actually easier. So I'll do the answer as if I did Binomcdf. So Binomcdf, since I want between 4 and 6 inclusive, what that means is 4, 5, and also 6. Or really 4, 5, or 6. So 10.75 and 4 for Binomcdf, plus Binomcdf of 10.75 and 5, plus Binomcdf of 10.75 and 6. Those are the only 3 I need. That's not too bad, particularly compared to the previous ones that would add 5 or 6 of these things. This is only 3 of them. This one I'd probably do myself with just those 3. So I would go to the calculator and go and get Binomcdf with 10 trials, 0.75, and 4. Paste that, and then add that to the next one. So I do all 3 of these at once. So I already did 4, I then do 5. So I then have Binomcdf of up to 4, then up to 5. Then also add up to 6. So I have all 3 of those. Put all 3 of those together, we get 0.221. Or 22.1%. This can also be done using Binomcdf. This one's a little bit trickier though. If you notice, I want some things that are less than or equal to 6. So what I could start off with is Binomcdf, or in this case CDF rather, Binomcdf of 10.75 and 6. This would calculate the probability of every value up to and including 6 and put them all together. But I only want a couple of those. I only want 4, 5, and 6, which means I don't want 0, 1, 2, and 3. So what I could then do is say, all right, well, take Binomcdf and take away Binomcdf up to 3. That way, where Binomcdf would say take all the probabilities for 0, 1, 2, 3, 4, 5, and 6, and then CDF says take away 0, 1, 2, and 3, the only things I have left over are 4, 5, and 6, which is what I got here. If I run that I'm just quickly getting these again from vars running A and B. So if I run CDF, 0.75 and 6, and I then subtract away the same function, Binomcdf, but up to 3, so I take away those values, I should get the exact same answer, and I do. Approximately, there's a little bit of round-off error way later, but that's not as much. That's not as relevant for us. That's just round-off error. So, not a problem. This still comes out to be approximately 0.221 or 22.1%. And as you may expect, we would then interpret it using the more or less same sentence. I'd expect in this case, I'd expect between 4 and 6 flights to be on time in about, we have 22%. So I'd expect about 22 of those repetitions. So that gives me my answer for E. All right, lastly for this problem, we have F. Would it be unusual for all 10 flights to be on time? Which is, I guess, one word. Shouldn't be, but whatever. Well, we want to see if it's unusual for all 10 flights to be on time. Well, let's find the probability of all 10 flights being on time. That means that we need to find Binomcdf. If I have 10 trials with probability of success of 75%, I want to see the likelihood of all 10 of those being on time. So I'm going to go and run Binomcdf for 10 trials, probability of success, and in this case I want to see what the likelihood of all 10 of them being successes are. I run that and I get a pretty small number. I get about 0.056 or 5.6%. Unfortunately, we have that 5.6% is bigger than 5%. So this is not unusual. So that would be our conclusion here. It is rather small. It is a rather low percentage, but it's not low enough to really be considered to be unusual. This isn't that weird. So that'd be our answers for that problem. All right. I want to do the next page as well. If you wanted to go through any of those questions again, you can always rewind and rewatch if you want to see how I did anything there. I have all my answers, though, written out here of like what functions I use, etc. All right, so this next question here with covering people's mouths, this one we only have 3 questions to answer, so not as many. According to a study done, the probability a randomly selected individual should say cover his or her mouth when sneezing, also spelled wrong, is 0.267. So the likelihood that somebody will not cover their mouth when sneezing is 26.7%. Suppose you sit on a bench in a mall and observe people's habits as they sneeze. Notice that sneeze is spelled correctly. We have, what is the probability that among 10 randomly observed individuals, exactly 4 do not cover their mouth? Now, this is already assuming that it's binomial. However, we should be able to confirm that it is. Because if I had this question, I should need to be able to tell, is this binomial or not? Can I use my functions for that? So, looking at the situation, covering B, which is binary outcomes, we have these individuals are either closing their mouth, or, they're covering their mouth, or they're not covering their mouth. It's one of the two. So it's binary outcomes is fine. I being independent, it's probably the case that people don't influence each other too much. One person covering their mouth probably is not going to influence another one covering their mouth. You could argue that one, but we're going to hopefully have that one let slide. N being fixed, what is the probability that among 10 randomly observed individuals, so N is 10 in this case, so it is fixed. And the probability of success is indicated to be 0.267. There's no indication that changes as trials progress. So the probability of success seems to be the same. So it is binary. We can use our binomial probability. If you haven't already, try A, B, and C by yourself. So pause the video, try A, B, and C, and see how you do. And then you can unpause the video, come back to this, and see if you got similar answers. All right, but I'm going to continue forth from now. So what is the probability that among 10, exactly 4 do not cover their mouth? Since it says exactly, I need just one probability. I don't need a multitude of them. So I can just run simply Binomcdf. Again, PDF is only for exact probabilities with 10 successes or 10 trials, a probability of success of 0.267, and then a number of successes to be 4. So I can run second vars, go get Binomcdf near the bottom, and run it with 10 trials, 0.267, and 4 as my number of successes. Run that, I get 0.166. I'll type it over here. Equals 0.166. Approximately. Or 16.6%. So that'd be my probability. Doesn't ask us to interpret, so we're done with that problem. What is the probability for B that among 10 randomly selected individuals, so still 10 trials, fewer than 3 do not cover their mouth? Should say cover. So fewer than 3, what that means is 2 or less, or 0, 1, and 2. 0, 1, and 2. That's what the phrase fewer than 3 means. So I could actually do this by doing Binomcdf of 0, and then Binomcdf for 1, and Binomcdf for 2, and put all those together. Or because I really just want to go from 0 up to something, I can simply run Binomcdf. It's a little bit faster. In this case with 10 trials, 0.267 probability of success. And in this case, we want to include only up to 2. So I'm going to just say 2 as my number of successes. If I were to put 3 there, what that would do would also include 3. But we want fewer than 3, not fewer than or including 3. Which would be something like at most 3. So, should be able to run that. Gonna go run Binomcdf yet again in second vars. Here, 10 trials, 0.267 probability of success, and up to 2 successes. We get a probability of about 0.475. Or 47.5%. And I'm typing in the wrong place. Over here, 0.475 equals 47.5%. So that's what we're looking for that question. Lastly, would you be surprised if, after observing 10 individuals, fewer than half covered their mouth when sneezing? So, after observing 10 individuals, still trials of 10, fewer than half covered their mouth when sneezing. Well, fewer than half covering their mouth, we have probability that somebody not covering their mouth is 0.267. That means the probability that they cover their mouth is 1 minus 0.267. Or, in this case, 1 minus 0.267 is 0.733. So that's the likelihood of them covering their mouth. Well, if it says fewer than half covering their mouth, then I can consider that then Binomcdf, because fewer than half would be 0, 1, 2, 3, or 4. That'd be less than half of the 10 individuals. I can do that with 10 trials, probability of success of 0.733. In this case, success is actually covering their mouth. And then up to 4 individuals. If I run that, Binomcdf of 10.733 up to 4, I get 0.27. So 0.027 rather, or 2.7%. Since 2.7% is less than 5%, then we would consider this to be unusual. Now that is one way of doing it. Another way of doing it is considering the same probability here. If we want fewer than half cover their mouth, then that means with those that didn't cover their mouth, then that means we had at least 6 people not covering their mouth. So we could also do this if you wanted to instead as Binomcdf of 10, our original probability of 0.267. And then I want to consider at least 6 individuals. That way I have, or really at least 5 individuals. Actually at least 6. That way we have also the fewer than half are covering their mouth. So what I actually want is up to 5. I want to take that away from 1 is another way of doing it. If I do 1 minus Binomcdf up to 0.267 and up to 6, should get approximately the same thing. Oh wait, no, up to 5. What am I doing? Should get up to 5, and there we go, 0.027. So this also gives you 0.027, or 2.7%. Notice what I did in that second one. I was considering, okay, well, fewer than half covering their mouth. What does that mean for those that didn't cover their mouth? Well, if fewer than half cover their mouth, then that means more than half didn't cover their mouth. So I want to find the likelihood that more than half, which means 6, 7, 8, 9, or 10 of those 10 individuals did not cover their mouth. And unfortunately, Binomcdf only goes from 0 up to something. So if I want to find 6, 7, 8, 9, or 10, I can take away 0 through 5, which is what Binomcdf up to 5 does. I could take that away from 1, and I get my overall answer there. So I get my overall answer, 0.027. I think the first way is a little bit easier, first doing the complement. Either way, a complement is going to be necessary at some point. It just depends on how you'd like to approach it. Either way, that's it for this section. I just wanted to give you a couple more examples of Binomcdf if we did not get to enough of them in class. And you can always refer back to this video if you're having trouble with any homework problems or if you want to study more. I hope this helped. Again, just keep in mind what the 2 different functions are for. You can always rely on Binomcdf if you ever need to. That's perfectly fine. It works for all situations. I could have done Binomcdf for all these. I did Binomcdf instead. I could have done Binomcdf for 0, 1, and then also 2 and add them all up. And I would still get the same answer that I did in part B. So I can do Binomcdf for all circumstances. It's just that Binomcdf can be far more useful in certain cases where you would just be doing Binomcdf way too much, and it just becomes kind of annoying. So Binomcdf is to help to be convenient in as many cases as it can. Just know what each of those functions are, understand what binomial means and how to determine binomial, and you should be fine with all this. Anyway, I hope this helped, and if you have any questions, feel free to ask me outside of class or to put them in the comments. With that said, I hope you have a good day.